Hey everyone, welcome back. I am absolutely thrilled to have you here for another explainer brought to you by Forge College. If you've been following our track on transitioning from Ethereum to Solana, you know we've been fundamentally rewiring how we think about smart contract security. Today, we're taking a huge step. We are stepping completely out of the familiar, gated community of the Ethereum virtual machine and walking straight into the wild, open market neighborhood of the Solana virtual machine. We're going to get an overview of SVM-specific attack surfaces. It is a brand new landscape, and trust me, the rules of engagement have completely changed.
Okay, let's dive right into this. Have you ever seen an experienced EVM developer wake up in a cold sweat? It usually happens the exact moment they realize there's no global MSG sender in Solana. I mean, in Ethereum, you have this incredibly cozy, implicit global state. The EVM essentially holds your hand, telling you exactly who called your contract and automatically isolating your storage for you. But on the SVM, yeah, that hand-holding is entirely gone. Instead of the network implicitly granting access based on who called you, you are basically handed a list of accounts, and you have to manually check who owns them, who signed for them, and whether they're even the accounts you asked for in the first place. It's a total paradigm shift.
Following our previous lesson on permissions and access patterns, today's agenda is basically going to be our engineering blueprint. We'll cover welcome to the SVM, core attack surfaces, EVM versus SVM checkpoints, anatomy of an exploit, writing secure code, and we'll wrap up with takeaways and next steps. All right, let's kick things off with Section 1, Welcome to the SVM, the Open Account Passing Bazaar. So I like to think of Ethereum as a highly secure, gated community. You have a key, you walk up to a specific house, and the system knows exactly who you are. Solana, on the other hand, it's an incredibly fast, highly parallelized, open-air bazaar. Accounts are just constantly being passed around directly from program to program. And here is the absolute core security mindset shift you need to make today. On Solana, your program does not implicitly gain access to anything. Instead, a user's transaction hands your program a curated but totally untrusted set of accounts. Think of these accounts as closed boxes. In the SVM, literally anyone can walk up and hand your program a malicious, cleverly disguised closed box. If you don't explicitly verify what's written on the outside of that box and check the signature before you open it and use what's inside, you are absolutely going to get exploited. Moving on to Section 2, Core SVM Attack Surfaces. Let's look at exactly where these vulnerabilities hide when accounts cross program borders. And that brings us to our most critical definition, the cross-program invocation, or CPI for short. A CPI is a synchronous call where your program passes a discrete list of account references over to another program. You literally have to treat CPIs as a first-class attack surface. Why? Well, because this exact handoff, this runtime boundary, is exactly where a hacker will try to slip in a fake account if you aren't paying incredibly close attention. When you pass accounts over a CPI, any assumptions you made about ownership or signer status can be totally invalidated if you haven't locked them down properly. Section 3, EVM versus SVM checkpoints. And this brilliantly illustrates the direct comparison between what you know from Ethereum and what you must build in Solana. Let's walk through this matrix row by row. For caller identity, EVM gives you MSG.sender. SVM, on the other hand, gives you signer bits on a per-transaction basis. For state access, EVM uses isolated contract storage tied to the address itself. SVM, you're passing accounts as raw references, which means verifying account ownership is entirely on you. For cross-contract calls, EVM uses message calls or delegate calls with a global context. SVM uses those synchronous CPIs we just talked about with explicit account lists. And finally, permission checks. In EVM, you generally check this once at the contract level. But in SVM, the runtime gives you the metadata, sure, but you have to explicitly enforce those checks inside your program's logic every single time an account is touched. Section 4, Anatomy of an Exploit. Let's look at the local hazards in our new neighborhood with 3 concrete ways developers get robbed. Exploit number 1, missing ownership checks. Imagine Program A receives an account and just assumes it belongs to Program B. Program A then issues a CPI to Program B, but completely forgets to check the owner of that account first. Now, an attacker notices this, they construct a transaction, but they swap out the real account for a malicious account they own. Because Program A trusted the input without asserting the owner, it gladly passes the poisoned account right along to Program B, resulting in corrupted state or, worse, drained funds. You simply cannot trust an input just because it fits the shape of what you asked for. Now, I know what you might be thinking, but wait. What if the attacker just fakes the signature to get past my checks? Well, here's a really fascinating thing about Solana. The cryptographic signatures are actually attached and verified at the transaction level by the runtime before your program even executes. But, ironically, that actually leads us straight into our next major vulnerability. Exploit 2 is signer bit confusion. Say your program accepts a writable account, and you notice the signer bit is set to true on an associated authority account. You might naturally think, great, they signed it, they authorized this action. Danger. No way. You cannot conflate the mere presence of a signer bit with semantic authorization. An attacker can craft a transaction and sign it with a completely different private key just to flip that signer bit to true. If your program doesn't explicitly check which key actually signed it against a protocol-level delegation record, you've just been tricked into accepting false consent.
And exploit 3, control flow sequencing. Honestly, this one is super sneaky. Program X calls Program Y via a CPI and passes along an account. Now remember, CPIs are synchronous. Before control returns to Program X, Program Y might reorder its internal rights, or even chain another CPI that mutates that shared account. When control finally returns, Program X goes ahead and makes calculations based on the old, stale state from before the CPI. If you chain CPIs without defensive sequencing, mutable accounts can be entirely altered right behind your back.
Section 5. Writing secure SVM code. It is time to install some new locks on our doors with some secure Rust code. It all starts right at the entry point of your program, the process_instruction function. When you pull accounts from the accounts array using the iterator and next_account info, you basically have to look at that list and assume every single item is highly radioactive. It is entirely untrusted input. You must manually verify every single assumption before proceeding. Now, what's really interesting about this slide is how simple the fix actually is. Notice this single line of Rust code, if not signer_account.isSigner, return an error. By explicitly checking this, you enforce that the Solana runtime actually marked the account as having provided a valid cryptographic signature. You're confirming real intent rather than just blindly trusting the account's presence in the list. Right after that, you implement the owner check by writing if target account.owner is not equal to CPI program account.key, you totally neutralize the account substitution attack we talked about earlier. You are actively verifying, hey, this data box I was handed, it was actually created and is owned by the program I'm about to call. If it's not, you throw an error and halt the whole transaction. So let's see how this builds into a strict, non-negotiable validation order. 1. Pull the accounts via the iterator. 2. Verify the is_signer status. 3. Verify the target_account owner. And only then, at step 4, do you construct and invoke your cross-program invocation. Exact ordering is absolutely critical here, guys. You must validate the signer and the owner before you ever build or issue the CPI to prevent irreversible local state changes. All right, Section 6, takeaways and next steps. Let's lock in these core principles for threat modeling the SVM. So the crucial point here is really a combination of these 3 principles. Number 1, treat every single CPI as a brand new security boundary. Don't trust anything implicitly. Number 2, validate semantic authority. Don't just look at a signer bit and assume consent. Verify who actually signed it. And number 3, structure your control flow defensively. Anticipate that synchronous CPIs might mutate your state, so lock down your invariants. Explicit account capabilities are the beating heart of SVM security. Well, that brings us to the end of this explainer. Next up, we are going to get even more hands-on with CPI and account validation risks, where we'll be analyzing real anchor handlers line by line. Your homework? Go find a Solana program on GitHub right now and see if you can spot their CPIs. To master more Web3 topics like this, make sure to visit Forge College. This explainer was brought to you by Forge College. Thanks so much for learning with me. But before I go, ask yourself this. If explicit capabilities are the beating heart of the SVM, what exactly happens when a single corrupted account gets passed through a chain of 5 different programs? Think about that, and I'll see you in the next one.